So a little bit on my background. Before joining Infleqtion, I was a longtime IBM person, like 39 years. And the last 5 or 6 years I was with IBM Quantum. So they do a superconducting approaches. And I will say when I was there, if you looked at quantum computing, the entire world was golden chandeliers everywhere. And I think we did a very good job of maybe having a lot of people in the world think that that's all there was to quantum computing, that is a superconducting approach. As it turns out, that's not true, and it's very far from the truth. And the reason is because, of course, this is all based on quantum mechanics, as are, by the way, you and everything in this room. The physical world down to the atomic and the subatomic level is quantum mechanical. And so therefore it makes a lot of sense that when we think about quantum applications, and quantum computing is really just one of them, people would explore a lot of different approaches to how to do any given one of these. And so about 1.5 years ago, because I'd been at IBM so long, I decided to do something different, and I joined Infleqtion, and we do what is called a neutral or a cold atom approach. And as I go through this, I'm going to try to talk a little bit about some of the, if you will, the classical computing themes that we also see here at OCP. So first of all, quantum spans a very broad range of technologies, some of which have been in common use since the 1970s. If you've ever had an MRI, for example, on a shoulder or your knee or something like this, that is a quantum technology. In fact, a lot of the terminology when you get into an area like quantum computing, T1, T2, all these sorts of measurements, go way back to the 1940s. So, quantum, while we are still very far from being where we need to be, particularly in computing, has been going on from a practical perspective for 80 years, and then a theoretical perspective going back to the early 1900s. So yes, quantum is being explored for computing, but it's being used for atomic clocks, has been since the 1960s, radio frequency receivers, and I'll talk about both of those, but also highly sensitive inertial sensors, accelerometers. How fast are you going? How fast are you rotating? Measuring gravity. A very broad range of technologies that are explored with this. Now, in our case, we do neutral atoms. And so a neutral atom is not an ion. That is, it is electrically neutral. And typically, in these approaches, we use cesium or we use rubidium. Some other people use strontium and a few others. And by moving these atoms with lasers, and by first cooling them with lasers, so this was kind of a radical idea. Guess what? With quantum, you don't need giant freezers to do everything. You don't need cold plates. You don't need things like this, because if you have properly tuned lasers, you can cool atoms down to close to absolute zero, because the speed of the atom is proportional to its temperature. So if you can slow the atom down, it gets colder, which is very good for therefore making it have the quantum effects that you want it to have when you shine additional lasers at different frequencies at it. Which means that you can now start moving atoms around geometrically in three-dimensional space, and you get different types of characteristics. For example, if you put them in a ring, you get a gyroscope. So if you know what a laser ring gyroscope is and how that works with lasers, this is a normal extension of that idea using quantum ideas such as superposition. Highly more accurate. Every commercial plane that you've ever been in has had a laser ring gyroscope, and eventually they'll have these as well. Quantum computing, well, what we do is we lay the atoms out in a checkerboard, right? So they're not in a chip per se. They are in space, in a glass cell, like the one on the right-hand side. That glass cell is about 2.5 inches tall. We shine lasers, again, of appropriate frequencies in from the sides at different times once these atoms have gotten into the glass cells. And we can cause different effects, either one-qubit effects, if we're doing a quantum computer, or by taking advantage of what's called Rydberg atoms, where we take one electron on an atom. We all have this idea, right? There's the nucleus, and then there are the atoms. that exists somehow in a probabilistic cloud around the atom. Well, if you can take one of these electrons and pull it up pretty far away from it, right, you get a Rydberg atom. And now you can start combining Rydberg atoms in different ways to give you 2 qubit gates, but you can also use them for radio frequency receivers because you can push this electron in different places, and then with lasers of different frequencies, you can measure different things. So no glass chandeliers required, no golden chandeliers required. And of course, atomic clocks as well. Now, a lot of this goes back to work that took place at the end of the last century on what are called Bose-Einstein condensates. And what happens is when you take certain of these types of atoms and you cool them down, so you think of a clump of atoms, and you cool them down close to absolute zero with lasers, they now start to behave like a single quantum particle, which means they themselves can go into superposition, they can exhibit interference, and you can have entanglement as well. And it is this property of, if you will, making quantum matter with this that you then get all these types of applications that you can then apply. A lot of this initial work was done in Boulder, Colorado. The first atomic clock, in fact, the most accurate atomic clock in the world is in Boulder, Colorado. It's a little different from the way we think of where leading edge technology is happening, but in fact, much of the quantum technology that is being developed today is done in non-usual places, if you will, at least when we think back to the birth of the semiconductor world and so forth. So let's talk a little bit about quantum computing. Once again, on the right-hand side, as I've described it, there is an atomic prism, a glass cell. We create a checkerboard, if you will, a square of atoms. In the lab, we have created a square, a checkerboard, with 1,225 atoms. Now, these are proto-qubits, to be very clear. These are not fully controllable qubits. But to give you an idea, that little square of 1,225 atoms, think of them as qubits, fits in the width of a human hair. So as we think of scaling and chips and things like this, it's very different ways we have to think about this, as well as cooling. In fact, once we get above 1,000, we do need a little bit of cooling, but not the massive amounts that are discussed here. On the left, I'm showing you the software stack. Now, look, software stacks are software stacks. At the bottom, you talk to the hardware. At the top, you have applications. In the middle, you have different levels that are convenient in different ways. And to one question before, this is what we train people on, right? So how good are the libraries that let you do what you want to do? The libraries at the bottom are going to be very hardware specific, even though we might generalize some of these things. But as we get toward the top, we hope to have reusable libraries that are valuable in particular industries, such as financial services, things like this. Now, a couple of comments on quantum computing. The state and the immediate future of quantum computing is very controversial. Many people will say, we're just on the verge of quantum advantage, where quantum computers will do significantly better along with classical computers than classical computers can do before. We saw your chart before between the optimists and the pessimists, and somewhere in the middle are the realists, right? When you actually have to build these things. So you have to take a lot of statements about how imminent is the advantage with a grain of salt. And what ends up happening, as we've seen here with OCP, is ultimately we really will need benchmarks, right? We'll need benchmarks, Heather, I'll pick on you, from analyst firms, but also other organizations, because vendors will be vendors. Vendors would like to make money. Vendors would like to sell you something and still keep getting more and money. So we're going to need that type of work to be able to have a reasonable apples to apples comparison of this. And I also do believe it's time we start thinking of some of these power and sustainability questions. I don't think we have to wait on this. Now, to one question before, though, you can't compare a quantum computer to an HPC system per se, because if a quantum computer is doing something that is impossible to do classically, what is your classical number? Is it infinity? Right? So it's a little tricky on how you do these things, but at least within the quantum realm, if you will, we do have to have some idea of these things. Because frankly, it might be worth it in some cases for this quantum computer to take a little bit longer than that quantum computer if this is using significantly less energy. And those are the questions we need to now start having answered. Now, a little bit more on the software. We are not going to get to this fabled quantum advantage until we have really great software that optimizes this. A classical computer deals with logic circuits, bits. Quantum computers deal with qubits, quantum bits. Compilation is a whole new game out there. Optimizing compilers for quantum is a great PhD topic. Optimizing compiler for classical, not so much anymore, right? It used to be, but not so much anymore. And so there's a lot of significant work that's being done by either software companies or software divisions within quantum companies to do this. We acquired a company called Supertech out of the University of Chicago last May to do exactly this, starting with quantum computing, but now then to start thinking about software on other types of quantum devices. And so this includes atomic clocks. Now, why do we need more clocks? Well, generally speaking, greater accuracy is always a good thing. And greater stability, clocks that stay accurate for a very long period of time. Now, when I first started getting into this, you know, like you, I've used GPS for years. I never thought of GPS in terms of time. And then someone pointed out that that timestamp on your ATM receipt probably came from a GPS satellite. But they're very unstable. They have to be corrected twice a day from Earth. Now, that's not going to work if you're in the military and you're worried about a ship or a plane or a submarine or something in space where you have these numbers of errors that are accumulating. And it's time. You can't measure speed. You can't measure speed of rotation without accurate clocks, right? So clocks are at the core of much of what we do in terms of positioning, navigation, and timing, as well as things like data centers, right? Financial transactions. So clocks are going to be really at the core of an awful lot of these things. Now, GPS spoofing, that is where someone says, look, you know, here's where you are, and you're not actually there. Or even worse, it says, we don't know where you are. I used to think this was FUD. It's not FUD. It's happening all the time now. It's happening in the Taiwan Straits. It was happening in Israel. I'm sure it is happening right now. It's a serious problem. It's getting to the point where we have to make sure that we can allow for at least backup systems to give us accurate positioning. And so atomic clocks will be at the core of this. Now, quantum RF, quantum radio frequency receivers. This is the idea of using these atoms with their Rydberg states to detect electrical fields. And the ones we care about here are RF frequencies. And it's been demonstrated by quite a few people around the world that this is a viable method for doing this. It's much more accurate, it's much more selective. The size of the receiver, the size of the antenna doesn't grow or shrink as your wavelength or frequency changes, right? So it's much more accurate to do these types of things. And so as a result, it's going to replace all these different types of receivers over time, right? Not instantaneously, but over time. As you think of all the different bands that people use for different types of applications, and in particular, defense agencies do care about this. If you look at any military ship around the world, maybe you might expect to see guns or whatever. The main thing you're probably going to see are antennae of different communications bands to do this. I've been told some of them have over 50 different antennae for different frequencies. Now, we use 2 frequencies alone just in our mobile phones. So ultimately replacing this, having more accurate, more sensitive, smaller receivers that use much, much less power than these huge things are going to open up a whole lot of new applications. So just a little bit at the very end here, just about Infleqtion. We were born as ColdQuanta in Boulder, Colorado. We now have about 220 employees. We have been traditionally a hardware company, but we're now shifting to software. And just returning to this idea of software, it's easy to imagine it for computing. But for all these types of things that we've been talking about receivers, quantum sensors, right? They're generating quantum encoded data, which is very hard to get, very expensive to get from classical data. And so we will want to move this. So pointing toward a later talk about quantum networking, moving quantum data from one place to another is going to be an essential technology for any of this, any of the quantum computing to work. So call to action. There's a lot more to atomic clocks than you may think about. I suggest you learn more. Radio frequency receivers are going to be key. And this one technology, neutral cold atoms, in addition to superconducting, in addition to ion trap, in addition to quantum dots, in addition to nitrogen vacancy, all the different ways of doing quantum are fascinating ways of implementing this technology. So thank you very much.
We have time for one question, if anyone has a question for Bob.
Quick question on the atomic clock side of things. Certainly Symmetricom and company have had the rubidium clocks for some time.
Mm-hmm.
What's the difference between that technology and what you're talking about here? Are you talking about size? Where's the distinction? So
the distinction is that they're going to be much smaller, is the idea. Within 10 years, we expect that these will be about this size, right? About this, let's say the size of half the size of a phone, right? Would be the size to which we'd be able to reduce. Within two to 3 years, we expect to have them rack mounted with very high accuracy. Within 2 years after that, we expect to get them for the military specifications for rack mounting. Military is going to be, defense is going to be one of the main customers. And by the way, across the board with quantum, that is true. These are all dual purpose technologies. And the military in the very short term, for reasons you can guess now, are going to be key to it. So that is our goal in about 10 years, to have this sort of accuracy and something about this big. So.
Okay, thank you, Bob. Thank you, Bob.